Hi everyone, my name is Fenwei Hang. This presentation is an overview of a paper we submitted to the Journal of Hydrology. My co-authors include Professor Ethan Yan at Lehigh University and Kyung-Ho Song at Pacific Northwest National Lab. In this talk, I will focus on human adaptation and its impacts on water scarcity uncertainty in the Colorado River Basin. This research is supported by the Sloan Foundation and National Science Foundation. To give you some background information, the Colorado River Basin is one of the most important water systems in the western U.S. It supports water supplies for 40 million people and 5.5-acre farmland. Among various water uses, about 80% of the water is consumed by agriculture. However, the extensive drought since 2000 has caused a serious problem for water security due to the declining water levels in Lake Mead and Lake Powell. This year, the water levels in both lakes has dropped to the historical lows. As a result, the Bureau of Reclamation announced Tier 1 shortage for the first time in history to cut water consumption starting next year. Despite the efforts to delay the decline in water storage, many experts expect further cut in water supply will be needed if the drought continues. As climate change is driving the Colorado River Basin to a drier condition, we wonder how humans will respond to it in terms of water consumption and what we can learn to improve the basin's water resource management. To address this challenge, our goal is to build a model to simulate the water system dynamics, including human adaptation to facilitate policy development. The first step toward building such model is to conceptualize the water system and identify the key components driving the evolution. Since agriculture consumes about 80% of the Colorado River water, for simplicity we only focus on modeling agricultural water use and farmers' adaptation to climate change. Let's assume this is the Colorado River Basin. The flow is originated from snowmelt in the Rocky Mountains. We have a series of dams for water supply and power generation. Farmers can withdraw water at different locations. The system is stable when the water resource is abundant and supply is greater than demand. However, climate change has caused decreasing stream flow and declining water storage in the lakes. The perceptions about climate change can stimulate human behavioral change. In addition, the dynamic impacts of climate change may vary at different geographical scales, which further complicates the problem. In terms of modeling, we consider two submodels, a water system and a human system. The water system simulates the hydrological responses and the water allocations under future climate scenarios. The human system, on the other hand, simulates learning and water consumption decisions. The changes in water uses can affect water storage and distribution in the basin, whereas water redistribution and climate change can then influence human perceptions about future water availability. We believe this is an important perspective, and that the modeling can provide valuable information to support water resource management. As an attempt to solve this problem, we developed a couple agent-based modeling framework. In this presentation, I will briefly talk about the coupling framework and how we applied it to quantify water scarcity uncertainty in the Colorado River Basin. Since we do not have much time, I will not go into details about the math, but provide the general ideas of the method. The coupled modeling framework consists of a water resource management model and an agent-based model. The water resources management model applied here is the Colorado River Simulation System, also known as CRSS. The CRSS is capable for simulating future climate and hydrological conditions. More importantly, it has a set of rules to simulate dam operations and water allocations in the Colorado River Basin. Therefore, it is the best available model for this task. The agent-based model adopted a reinforcement learning algorithm to simulate agricultural agents' decisions and adaptive behaviors. Basically, the reinforcement learning agent seeks to maximize their long-term rewards and may occasionally choose to deviate from their optimal action to detect environmental changes and improve their water consumption strategy. Depending on the feedback from the water system, agents may regret if they did not receive the requested water quantity and consequently change their actions when facing the same situation in the future. The CRSS runs on a monthly time step. In every December, it provides water supply and climate prediction information to the agent. Upon receiving the information, an agent will run the reinforcement learning algorithm and submit a water demand request to the CRSS. Then the CRSS will allocate water to the agent for the coming year based on its request and the water availability. Let me provide some more details of the agent-based model. An agent has 6 parameters, 2 for modeling the randomness in human decision-making and 4 for learning. An agent's action is to increase or decrease water consumption, and the quantity of change follows a half-normal distribution with mean, mu, and variance, sigma squared. The 4 parameters for learning are exploration rate, learning rate, discount rate, and regret. The exploration rate epsilon is the probability for an agent to deviate from the optimal action to detect environmental changes. The learning rate alpha represents how much the agent believes in the new information. Alpha equals to 0 means an agent does not learn, and alpha equals to 1 means the agent only trusts the new information. The discount rate gamma represents the relative importance of the future reward to the present reward. Regret is a multiplier for penalize the unsatisfied demand. Besides the 6 parameters, agents need to go through training to obtain a prior knowledge of the initial transition probability and optimal strategy. The training data is generated by Monte Carlo sampling of the historical data. The quantification of uncertainty requires many model runs. Due to the computational limitation, we developed a systematic process to select 5 scenarios for illustration. First, we identified the theoretical parameter ranges from the literature and randomly generated 2,000 parameter sets for each agent. Then, we evaluated the performance of the sets by comparing the simulated results with the historical data. If the performance of a set is better than a predefined threshold, the set is included in the behavioral set. Finally, we rank the behavioral set by performance and select a parameter set for each agent based on the ranking to compile a scenario. By this process, we compiled 5 scenarios from Q1% to Q99%. The Q1% scenario means that agents in that scenario use the parameter set ranked the lowest 1%. Okay, now let's take a look at the results. We simulated the couple model from 2019 to 2060 and repeated the simulation 30 times for each scenario. This figure shows the natural flow applied in the simulations. We use fixed climate input for all scenarios to focus the discussion on human adaptation. The natural flow is a drier than normal condition with 2 significant droughts in 2033 and 2047. Here, we choose a shortage year as the water scarcity metric. A year is a shortage year if the total basin outflow to Mexico is below the quantity stated in the 1944 Mexico water treaty, which is 1.9 billion cubic meter. The resulting water shortage years of the 5 scenarios are shown in the right figure. Overall, the results show a dire future for the Colorado River Basin and indicate that the basin may experience 13 to 30 years of shortage until 2060. However, each scenario predicts a different range. This is because the scenarios represent different hypotheses about human adaptation. If we can know better about human decision-making in terms of the parameter values, the uncertainty range may be reduced. For example, If we know that the Q99% scenario is the most likely scenario, the water shortage year range can be reduced to 13 to 20 years. As an example, let's focus on the Q99% scenario. This slide shows the water consumption aggregated to basin and subbasin levels. We simulated the scenario 30 times, and each line in the figure represents the results of one simulation. Judging by the ranges of the lines, we can see that the upper basin contributes more uncertainty to the basin water consumption than the lower basin. The upper basin and lower basin each entitles for 9.2 billion cubic meters of water, or equivalently 7.5 million acre-feet, as the black dashed line indicated. We divided the 40 years simulation into 3 periods of time, separated by the 2 drought years in 2033 and 2047, to discuss agents' adaptation behaviors. In the first period A, we can see that the upper basin water consumption increases steadily, and the lower basin consumption stays at the 9.2 billion cubic meter level. Consequently, the basin total water consumption also increases. This is because the lower basin has used up its proportion, whereas the upper basin still has plenty of room to increase their water consumption. Nevertheless, the increase in water consumption continues to deplete water storage in the reservoirs and make the water system vulnerable to droughts. The right figure shows the total basin storage. We can see that from 2029 to 2033, the basin storage drops significantly from 25 billion cubic meter to 8 billion cubic meter. When the 2033 drought comes, the basin no longer has water to satisfy the demand and has to cut water supply by 1/3. In period B, agents need to actively adapt to the low water storage condition and recover water storage. Therefore, both upper basin and lower basin consume less water than they were in period A. When another drought occurs in 2047, it triggers another round of adaptation in the Colorado River Basin. Given the experience of the period B and the normal flow condition, agents are in a better position to cope with the shortage. Consequently, the basin and the subbasin water consumption can quickly recover from the 2047 drought. The upper basin water consumption may even grow higher than the consumption level in period A. However, the lower basin never recovers to 9.2 billion cubic meter consumption level. This is because the lower basin relies on the flow release from Lake Mead, but the storage in Lake Mead remains low in period C. In addition to the uncertainty analysis, we also conducted clustering analysis to characterize agent behaviors and sensitivity analysis as a diagnosis tool for improving human system modeling. Due to the time limit, I will not talk about the result here. If you are interested, we can talk offline or through email communication. In conclusion, modeling human behavior has been a critical challenge in water resource field as an attempt to simulate human adaptation and its impacts on water scarcity uncertainty. We understand that there is plenty room for improvement. Our exploratory analysis aimed at leveraging the use of the model through uncertainty quantification to identify opportunities for uncertainty reduction and the model improvement. In the future, we are looking forward to including other sources of uncertainty, such as climate projection and other water uses, to provide a more comprehensive view of water scarcity uncertainty. In the meantime, we will consider conducting survey and interview with water users to improve human behavior modeling. With that, thank you for your attention, and I will be happy to answer your questions by email, online, or on site. Bye-bye.